Hello, everyone. Good afternoon. Um, Today, uh, our webinar is receiving Dr. Jing Wu. She is assistant professor at University of Rhode Island, and she is PhD. She received her PhD in statistics from University of Connecticut. She is interested in research like missing data, big data, survival, and longitudinal data. Doctor Who has published several articles in journals like Journal of Computational and Graphical Statistics, Statistics in Medicine, Statistica Sinica, Technometrics, JAMA Oncology, Journal of Clinical Oncology, among others. Her talk will be about online updating of survival analysis today. So, Jing, thank you for your talk today here.
Thank you,
You can start
Michelle.
as well.
Yeah, thanks, Michelle, for the nice introduction, and thanks, Mario, for inviting me to the seminar. My name is Jing Wu. I'm from the University of Rhode Island, and the topic I present today is online updating of survival analysis in a big data setting. This is a joint work with Dr. Minghui Chen, Dr. Elizabeth Schifano, and Dr. Jun Yan from the University of Connecticut. And again, please feel free to interrupt me if you have any questions during the talk. Right. And here is the overview of my talk today. So I will start with a brief introduction of big data and survival data analysis, right? And then I briefly summarize what we have done in the area of online updating for big data streams, right? And today, in today's talk, I mainly focus on our recent work in the area of survival analysis and also big data. All right, and so there are a lot of definitions for big data. One commonly used terminology are big data, data on a massive scale in terms of volume, intensity, and complexity. Right? In the 2011 Landis paper, they first introduced the 3Vs challenge in big data. So those 3Vs are volume, right, amount of data, right, velocity, speed of data read-in and output, and the last one is variety, right, the range of data types and sources. So I would say for computer scientists, probably volume and velocity are the most important important areas for them, right? But for us statisticians, we probably are more interested in how to handle different types of big data. All right, and there are other V's. For example, the fourth V's is veracity or even validity, right? Data integrity and the ability for an organization to trust the data, right, and be able to confidently use it to make crucial decisions. So this is also a very important feature of big data, right? And these days, people extended the 3Vs to even 42Vs, right? I skip here. If you're interested, you can visit this website. All right, so practically, right, how big is big? Right, in the 2012 paper, right, Emerson and Keynes paper, they mentioned like if the data are 20% of the RAM, right, we consider them as large. If they account for 50% of the RAM, then we consider them to be massive, to be huge, right? So even for 10% to 20% of the RAM, right, some software such as R cannot be used, right? So that that makes the big data challenge. That brings the challenge of big data for us statisticians. So even the simple algorithms such as linear model cannot be fit using R, right? If the data account for more than 20% of your RAM. Okay, and these days they are even growing more and more faster. So the recent methodology for big data in the statistics field can be grouped into 3 categories, right? The first one is we call subsampling based methods. So based on the name, we can tell instead of using the entire data, we take subsamples of the whole data set, right? Based on some rule, right? And then we process each subsample separately. You can either process them parallelly, right, using parallel computing, or you process them sequentially, right, like what we'll talk about later, online updating. Okay, and finally, we combine those results from all subsamples to give us the overall final result, right? And how to combine them to adjust the selection bias or some other issues is the key, right? And the second field for big data methodology is divide and conquer, right? This is also a very popular field. So basically, we partition a big data set into several groups, several blocks, right? And then we process each block separately, or we can also do in parallel. And finally, aggregate, conquer part. So we combine those solutions from the K blocks, right, and to give us the final solution to the whole data. Okay, and last one is the one we'll talk about today, right? Online updating method. So for a special and also commonly seen type of data, right, streaming data, this is the approach we'll use. So streaming data, they are data that continuously arrive in chunks, right? While we don't have enough storage to store all of those data. So instead, what we do is we store the key characteristics from the previous cumulative data, right? And when new data comes in, we combine the previous cumulative information and the current information to give us the new output. Okay, and yeah, we'll see this later. All right, so here is a diagram to visually show us how it works for the second group, divide and conquer. So suppose this is the problem, okay, and we divide it into several pieces, okay, more than 2. Yeah, here it's just 2, right? And for each sub-problem, we then solve it, okay, and finally, we combine those solutions from each sub-problem to give us one final solution. Okay, and so this is the divide part, and finally, this step is the conquer step. All right, and so for the online updating algorithm, right, here is one illustration. So the horizontal axis, you can think about this one as time, right, from the starting point, right, to time point 1, 2, 3, and it can be infinity, right? So for example, from starting point to our first time point, right, those are the data, right? And based on those data, we get our first result, right? And the output corresponding to the first result, right? And then move on to the second time point, right? We throw away those data. We only keep the output from the first time point period. Okay, and then combine or update the previous output, okay, using the current data from time point 1 to 2, right? And then that gives us the new output, right? And similarly, we throw away all those cumulative data, only keep those key characteristics, key information from the output at last time point 2, okay? And then combine it with the new data from time 2 to time 3, and give us the final update, right? So this is the flow of online updating. Okay, and so far we have developed online updating methods for statistical inference in linear model, right? Linear model is quite natural, right? Trivial compared with other models or other approaches, right? And then we also provide online updating method for estimating equation approach, right? And so for big data, right? Sometimes when data comes in, there will be more information than the historical data. We may have more variables, new variables, and how to accommodate those new variables in the online updating. That's another issue, and we have also done some work in this area. Yeah, and some other issues. So, so in this talk, I will just focus on how to do online updating for survival analysis, right? Which is not as trivial as the linear model. So, first, a quick overview of survival analysis. So the analysis of time to event data, we call it survival analysis, right? For example, you may be interested in the time to relapse of a disease, right, in medical research. And people in finance may be also interested in the time to default of a credit card. Or we are interested in time to death of our phone's battery, right? They are all problems of survival analysis. So it's not only a problem in medical research, but also a problem in, for example, biology, engineering, blah, 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 a lot of fields. Okay, and standard approach for survival analysis include Kaplan-Meier curve, log-rank test, and one of the most widely used model in survival analysis, right, the Cox proportional hazards regression model. Yeah, we call it Cox model. Right, so the challenge to conduct survival analysis, right, in the big data setting is, particularly here we are talking about online updating setting, is we continuously, right, or the data continuously arrives in, right, but we don't have access to the historical data, right, due to the storage limit or other issues. We don't have access to all the historical data. So how to update the cumulative information, right, when new data comes in, that's the challenge. All right, and so if we are allowed to have access to the whole data, then the conventional methods has no problem, right? But as we mentioned before, if it's more than 20% of your RAM, R will fail. And also, if we look at the conventional approach, right, for example, the partial likelihood estimator of the Cox model, right, well, the partial likelihood is given by this, right, xi is the covariates for the I subject. Beta is the regression coefficients corresponding to the covariate, right? And then exponential of linear predictor here, right? And then in the denominator, right, this RTI is what we call the risk set, all right, at time TI, right? Then includes all those subjects, right, whose survival time, either they are dead or they still survive, right, whose survival time is later than the survival time of the I subject, right? So, which means, right, in order to compute this quantity here, we need to store all of those information from the first subject, right? And that is not doable under the online updating setting, right? So how to solve this problem? So we address this issue by introducing a piecewise constant baseline hazard function in the Cox model. So before I show you the details, let's quickly take a look at the notations, and most of them are very standard. So suppose there are capital N independent observations, right? TI is the observed survival time. So it can be a censoring time, which means the person has not encountered the event yet, or it can be event time, right? Which means that you observe the event at that time, right? And the xi is the covariate vector. It can be a baseline covariate, or it can be a time-dependent covariate. which we also have some examples later in the real data analysis, right? And then delta I is the binary variable. So if it's 1, then that means the person encounters the event, right? Otherwise, well, it will be 0. Okay, so as we mentioned before, to address the issue, right, which requires us to storing all those data, we introduced the piecewise constant header function, right? And it looks like this. Okay, piecewise constant header function. You can think about this one just like a step function, right? For the interval from 0 to infinity, we partition it to j pieces, and within each piece, the function has the same value, right? A constant, and we denote it as lambda j. So this lambda j is also a parameter, like the beta, right? It's unknown and to be estimated, right? And then this is the interval, right? Within this interval, the hazard function takes the value lambda j, which is constant. Okay, so and then times exponential x beta, that give us the hazard function. This part is baseline hazard. Together give us hazard. All right, and then given that, then we can write out the cumulative piecewise linear hazard function, okay, which we will use to finally write out our likelihood function, and then we take log, okay, like what we always do, take log and then take MLE, right? And here it is. Here it is, and you can see the risk set is gone. The risk set is gone. Okay. All right, and then if we take first order derivative and solve for 0, then we get the MLEs. All right, and then second order derivative and negative, and then take inverse, that give us the covariance matrix. Okay, so far everything is standard, right? There's no fancy thing here. Everything is standard. Okay, and we assume, right, our software can handle the big data, right? If that's the case, then we can stop here, right? Otherwise, right, if the data number of sample size n is very large, right, and the previous one cannot be handled properly, then we'll need a new method. And first, here we proposed a new estimator called fixed partition estimator. Right, and then I'll quickly review what is online updating setting. So suppose the n observations are not available all at once, right, but arrive in chunks from a large data stream. Okay, and so for our first approach, fixed partition approach, based on name, right, we assume the partition for the piecewise hazard function is fixed for each time point or each accumulation point. Right, and then so we set the number of partition reasonably large, and then without loss of generality, we assume there is at least one event in each interval for each block of data. Right, otherwise it's not identifiable. Okay, so yeah, I will not go into the details, but just I will talk about the ideas behind it. So zeta hat nkk here in red, this is the vector of estimator based on the current block of data, the new data. Okay, and as we mentioned before, right, in addition to the regression coefficient, the lambda in the baseline hazard is also a parameter. So this zeta includes both of them. And H is the Hessian matrix of current block, right, in red. Okay, and the thing that we are most interested in is not the current estimator, but the cumulative estimator, right, based on all the data. Okay, and denoted by zeta hat k, right, in blue.
Jing.
Yeah.
May I have a question? Can I make a question?
Yeah, sure, of course.
When you say block, you mean, for example, the block of covariates at the instant t, or for example, you observe for some instance of times like t1, t2, tk, and compose this as a block, and then you prepare your estimates for this block.
Good question, very good question. So block here is a block of data, right? Or you can think about maybe in day one, the data is from day one's transaction, right? And then next day, right, the second block is day two's transaction. Okay. Yeah, so this is like a data, not the regression coefficients. Right? They are supposed to be the same throughout the block, but just we do not, and that's our goal. We try to estimate the final or update the final theta.
Okay, so you don't do it all the time that comes information. You kind of accumulate a few informations, and then you compute your estimate, and so on and so forth. Is it?
Yes. Yes.
Okay.
We don't
Thank you.
store those block of data. Right. Very good question.
Okay.
So,
thank you.
Yeah. So this is something we are finally interested in, right? The cumulative estimate theta hat k, right, which contains beta and lambda, right? And you can think about this one as a weighted average of the previous cumulative theta, right? And then the current estimator for the theta. So this is the new information. This is the previous cumulative information at block k minus 1, right? Or time point k minus 1. Right? And the weight here is the Hessian matrix, right? which is inverse of variance. So this captures the uncertainty of our estimator. Okay, and that's the idea, right? And based on that, we can calculate the variance for theta hat k to later on help us make inference, right? So the nice thing about this is then we do not need to store all those information, all right? We only need to store the cumulative estimate of theta hat, all right? And then the corresponding variance, Vk, right? And then cumulative Hessian matrix, Hk, right? Once we analyze the case block, we can throw other away, right? And then when k plus 1 new data comes in, then we just update those values, all right? And that's the key idea about online updating. All right, and so therefore we don't have the concern of limited storage because the dimensions of theta k, vk, hk, right? They are finite, and most of the time the dimensions are small. All right, so this is the first approach. Right, but there are several issues about the first approach. For example, right, we choose and fixed initial partition based on the first block of data. Right, that's the fixed partition approach. Right, at the very beginning, we choose the partition, and as new data comes in, we still stick with that partition. Okay, however, we cannot guarantee, right, the number of events in each interval will remain the same as new data come in. Right, so that assumption is very strong. Okay, so for the second approach, we assume that we can, right, make the partition adaptive. Right? We increase, specifically, we increase the number of pieces of the baseline hazard function by partitioning those intervals with a lot of events into subintervals. Right, so the nice thing about this is as the new data comes in, right, previously we don't have very fine partitions. And as more and more data comes in, the partition will be finer and finer. And ideally, it will approximate the underlying hazard function very well. Okay, if we have enough data, and which is not the issue for big data. Okay, so so for adaptive partition, I will quickly talk about the idea, just the idea. If you're interested, I can send you the paper, which is just recently published. Okay, so as we mentioned before, right, if that particular interval has a lot of events, right, then we partition that particular interval to 2 pieces. So before, the interval is a constant, just 1 line, right? If we cut it in 2 pieces, it will be 2 lines. So there will be 2 parameters to be estimated, and those 2 parameters are new. Okay, we never, we didn't observe them before, right? And so we assume the previous parameter lambda j is certain function of the 2 new parameters, right? And particularly, we just assume there's a linear relationship between those 3 parameters, and here it is. Okay, and then based on that, we can also calculate the expanded Hessian matrix. Okay, so to better help us write out those formulations, we introduce 2 expansion matrix P and Q. Right? One is applied on the vector, right? Theta hat. Right? The other one is applied on the Hessian matrix. Right? And the selection of P and Q is also very important. Right? In the later version, I will talk about how to select them. So to make sure that, actually I put it here, right? How to select PQ. There's a rule in order to reduce the bias of adaptive partition. Okay, and finally, we have the new estimator, adaptive cumulative estimator. It has very similar format as what we saw before, right? Weighted average. Okay, but here, the theta hat K-1 star here is the cumulative estimator from last update, well, which we expanded, right? And then this one is still the current estimator, so it's a weighted average, right? And the Hessian matrix, well, similarly, we also expanded because that's the matrix corresponding to the expanded theta, right? So, and you'll see Q here, P here, right? That's just a matrix that help us to make the formulation easier, right? But how to select them? This is the rule. Okay, and then we also have the variance matrix for the theta hat here. All right, so this is the second one, right? This is the second one. And the third version, which is another improvement of our first version, is the bias-corrected version. So for all those online updated algorithms, not only just for survival analysis, right? Inevitably, we'll introduce the bias when we do updating. Right, and the idea behind it is very natural because we never store the historical data. What we store is just the key characteristics. So again, inevitably, it will lose information, right? And how to make the loss, how to reduce the loss of information, we'll adjust that in the third version here. Okay, and so to reduce the bias introduced by theta hat, we consider the Taylor expansion of the score function for the current block, right? And after some derivation, which I skip here, we proposed a third estimator, bias-corrected estimator, right? And then still weighted average, but you'll see there's an additional term here, right? Which is the key for reducing the bias. All right, and then variance, all right, those are all standard, so I skip here. Okay, all right, and finally, so far we talk about the estimator, right, the bias-corrected estimator, right, and then the adaptive partition estimator. So a natural thinking is, why can't we combine those two together to give us the most optimal estimator, which allows for partition to be adapted and also corrected the bias, right, introduced by adaptive partition as well as when we do online updating. So there are 2 levels of bias. Again, one is from online updating, right, because we don't store all the data. Right? Another one is induced by adaptive partition, because when we do adaptive partition, basically we are introduce new variables that are never observed before. So there's another level of bias here. Okay, and finally, again, after some derivations and also some proofs here, we provide the last optimal version of the online updating estimator. Looks very similar, right? Weighted average, where the weight is the expanded Hessian matrix and also expanded score function, right? That act as the that term helps to reduce the bias. Okay, and then those are the four methods we propose. And to better see their performance, I first show you the simulation study, right? In the simulation study, we compare the performance of maximum partial likelihood estimator based on the entire data set, right? So this is the most accurate estimator, which we can use as benchmark because all data are used, all right? We don't throw away anything. Okay, and then we compare it with the four proposed method, all right? Fixed partition with or without bias correction, and adaptive partition with or without bias correction, right? All of those four approaches, they don't store the historical data. So every time when you do analysis, you just use the current block of data together with the previous stored information, right? And we generated 500 data sets, and the survival time, TI, independently from the Cox model, right? The hazard function is given by this, and later on we'll see it looks very complicated, but our methods can still recover it pretty well. Okay, and we consider three, well, in the simulation, we just considered time-independent covariates, three of them. One is continuous, two of them are binary. All right, and then, so for each block of data, because it's big data, so we consider pretty large data, 500,000 for each of those data set, right? And then the number of block, we cut them. Or you think about there are 200 days, right? So each day there are 2,500 new data. So together give us 500,000, right? And the censoring rate is 45%. 45%. Okay, so JK here is the number of pieces for the partition for the baseline hazard function at the case block, right? And for the first simulation study, we set the initial number of pieces equals 5, right? And for the fixed partition approach, right, we don't increase it. So J0 till the end, J1, they are all 5, right? And for the adaptive partition, the first partition is still 5, right? And later on, right, if the maximum number of events in certain interval is greater than a certain amount, greater than the average at certain rate, then we expand it. So we increase one piece at a time for each update until the total number of pieces reaches 50, right? 50. So this number is dependent on the total number of events, right? If you have a lot of events, then ideally you can make it very large. But if your data don't have a lot of event, right, high censoring rate, then you choose a maximum value. Okay, so first I show you the box plots of bias for the 5 types of estimator when we choose initial piece equals 5, right? So this block, this chunk of box plot is for beta 1, the continuous variable, right? And beta 2, beta 3, they are for binary variables. So binary variables comparatively have larger bias than continuous. MPLE, as we mentioned before, they are based on entire data. So it's the benchmark we'll compare with, no information loss, right? And then the first one, and then next to it is our first approach, fixed and no bias correction, all right? And then fixed and bias correction, and adaptive and no bias correction, and finally our optimal approach, adaptive and bias correction. Okay, and as we see, right, among all of those 4 approaches we proposed, the last one, adaptive and bias correction approach, give us the best results, right? It's almost no bias, okay, almost no bias, right? And then the third approach, adaptive and no bias correction, has the largest bias, and it's expected because it doesn't do bias correction for online updating, right? And by doing adaptive partition, right, it also introduced another level of bias. So, well, this one performs the worst. Okay, and then the standard error for those 5 types of estimator, they are pretty robust because we use the sandwich estimator, as we saw before. Okay, and the last one is the most interesting part. So in addition to the regression coefficient, right, most time we are also interested in the baseline hazard and then hazard function, which can help us to make a prediction or make further inference on survival. So here, the red curve is our true hazard function, right? The red curve is our true hazard function, and the blue one is the estimated curve, estimated hazard, right? And then the black one, they are the 95% confidence region, right? So this is approach 1, approach 2, approach 3, and optimal approach, right? So for approach 1, we can see the step function only have roughly 5 jumps, right? 5 jumps, right? And it doesn't really capture the shape or even the location of the real hazard function if it's complicated, right? And this one, adaptive partition, it can capture the shape, right? But because we don't do bias correction, so it's way off, right? It's not, the red line is not in the confidence region, right? And the last one is pretty nice, right? They almost overlap. The red curve and the red curve true curve and the estimated blue curve almost overlap. Okay, so this is the last one. Adaptive and bias one is our optimal method. Okay, and then one question we may have is then how to choose the number of initial pieces. So we focus on the optimal approach, and we vary the initial piece from 1, 5, 10 to 15. Okay, and here are the bias box for the box plots for the bias. Still, MPRE is the benchmark to compare with, right? And next to it is initial piece is 1, initial piece 5, 10, and 15, right? So we can see even for 5, right, it already performs pretty well. It already performs pretty well. So what it tells us is, right, if your data is big and it's streaming data continuously coming, right, at the very beginning, you don't need to assume a very complicated baseline hazard function, right? But as data comes in, then you update your hazard function, and finally, you'll still have the one you want, right? And this is especially important when your survival data has a limited number of events, right? So for example, real disease problem. So you cannot assume a very fine partition at the very beginning, okay? But if you have large enough data, then finally you'll see a very fine partition. Okay, and then again, pretty robust standard errors. And yeah, no matter which one, right, how many to start with, right, we have pretty good estimates for the baseline hazard function here. Okay, and those are the coverage probabilities for MPLE, and I just showed 2 here due to the limit of the page, right? And we'll see as number of partition increases, coverage probability becomes better, all right? And among all of those, the last one has the best CPs, approximately equal to 95%. Okay. All right, and the last part of this talk are 2 real data analysis examples. So in the first example, we consider the SEER colon cancer data, right, from this website. This is a very good website with all those information from 1973 till today, right? But I just used the data till 2013. Right, and among all those cancers, I choose colon cancer because this one is a highly curable cancer. So I set the maximum censoring time here as 18 months. So even the event happens after that, they are still considered as censored. Right, and under this setting, the total number of events, including both colon cancer and other cause deaths, is this amount. which give us a pretty high censoring rate, 80%. Right? So this is a real disease example. Not really real disease, but real event example. So which means we cannot assume a very fine partition at the very beginning. Okay, and the covariates we consider here for illustration, just two. One is a continuous variable year of diagnosis. Another one is a binary variable surgery treatment indicator, right? And then we cut the data into 127 blocks, right? And each block has roughly 2,500 data. All right, and we set initial pieces is 5 and increase it one at a time until total number of pieces reaches 14. Okay, reaches 14. And yeah, again, because we don't have many events, so we cannot make the maximum number of pieces too large. Otherwise, it will make it make the analysis unidentifiable. So here is the estimate and standard errors table. Right, well, all means we used the entire data. So this one is the benchmark we'll compare with, right? And among all those approaches, we can see fixed partition and bias correction and adaptive partition and bias correction approach. They are pretty close to those results from all data, from using the entire data, all right? And all those approaches have very similar standard errors as we saw before. Standard errors are very robust, even when the estimates are not. Okay, and then the estimated baseline has a function. So the black curve here are the ones based on the entire data. So we'll compare with this one, right? And then the red curve here is the one from our optimal approach, right? And we see yeah, the red curve is the closest one among all those four to this black curve. Okay, and well, since we have regression coefficient, we also have the hazard function, so we can make further inference. For example, we are interested in the estimated survival function for the two arms, right? Whether you receive surgery or not. Okay, and here it is. Here it is. Okay, and they are significantly different in terms of survival rate. Okay, and another example here is we use an example in finance. So we investigate the US-based venture capital-backed companies that received their first round of venture capital funding between 1946 to 2019, right? And this data involves this amount of companies. It can be potentially larger, but here we just focus on the US-based company, all right? And we consider successful exit, IPO, as the event, right? And then log of time as the survival time, log of days as the survival time, right? And also it has pretty high censoring rate, And the difference between this example and the previous example is, in the previous example, we only have time-independent covariate, right? And our method can also be easily applied to time-dependent covariate, which means the value of the variable change as time increases. Okay, so one variable we consider is the total number of funds received, non-funds, right? And another one is the cumulative amount of investment received at each round, cum amount. So this is time dependent. Okay, and then well, similarly, we choose the block size nk equals 500, right? And then initial piece, we change it from 1, 3 to 5, right? Until the total number of pieces reaches 15, then we stop increasing the partition. Right. And then MPLE again is our benchmark using the entire data, right? And then CUEE is another method proposed by our colleague. Okay, and you can see they compare pretty well, pretty close to our approach. Okay, but the thing with CUEE is they only give us estimate of beta, right? They are not, they cannot give us the online updating estimator of the hazard function, which we can do both. All right, and finally, estimated baseline hazard. Again, black curve is the one using the entire data, and the blue one is the red one is the one from the optimal approach. So those two curves are pretty close compared with the blue one, right, which is fixed partition and bias correction. Okay, and yeah, that is pretty much everything I want to talk about today, right? The detailed derivations of those estimators and their properties can be found in the paper I show later in the reference. And future work, we want to extend the current method to other types of survival data, for example, which allows for the relapse of the disease, right? And also which may not be the Cox model, right? And we are also working on online updating methods for other issues such as lasso and concordance measures, and so on. All right, and that's the end of my talk. And thanks everyone for listening. And any questions for me?
Thank you, Jing.
Yeah.
Let me open and see if we have any more questions. Any more questions, guys?
I see Mario.
Mario is trying to talk.
Yes, can you hear me?
Yes.
Yeah.
Oh, great! You could fix your microphone.
Yes. Hi, Jing. Thank you very much.
Hi, Mario. Thank you for inviting me here.
Okay. I have a question.
Uh-huh.
Does it make sense to think about the optimal block size?
Yeah, very good question. Yes, yes. We did some work in the previous linear model and estimating equation, right? And it turns out they are pretty robust. Of course, the number of block size is very important when we look at the rate of the bias, right? But the thing with survival analysis is a little bit more complicated. Not only just the block size, but also the censoring rate, right? If the censoring rate is high, then of course we'll need a larger block size. If the censoring rate is low, then maybe a lower block size will also perform pretty well. Okay, but a detailed or a rigorous derivation is a little bit challenging here, so we don't do it. We didn't do it. Yeah, but very good comment.
Okay.
All right. Are there any other questions?
I'm sorry, I was speaking with the microphone off. My microphone was off. I just asked this, but nobody could hear. Thank you for asking.
I have a question.
Okay, better.
It's okay? Nice talk, Jim. I like so much. But my question is, have you tried using another survival analysis methodology or only proportional risk Cox?
Yeah, very good question. So so far we haven't yet used other models, and that's one of the things in our future agenda, right? Other types of survival data and also other models. But here the Cox model, the reason we extend it to time dependent covariate is sometimes in my proportional hazard, something might be violated, right? But our method can also be applicable to time-dependent covariate, which even when the assumption violated, our methods can still work, right? But in terms of other model, like accelerated failure model or those things, we didn't derive the details, but our ideas can still be applied. Yes.
It's a good idea, né, to try different methodology, because it's different for introducing more data set during you use a methodology. It's good idea. I like this way, but I think it's so hard to to do. I think, but it's a good idea. I think it's a good idea to try to study different methodology.
Yes, yes.
Not only Cox.
Right.
Okay. Thank you.
Thank you.
Jing.
Michelle,
Yeah,
just one more quick question. Is it possible?
yes.
Yes, Mary.
Oh, Jing, what about a Bayesian solution?
Oh, it's always a challenging thing for Bayesian to handle big data, right? It's not just updating the likelihood part, you also need to updating the something. But for linear model, actually, they are very similar. So when you do updating the cumulative information, it's sort of like you are incorporating a new prior. Yeah, you're updating a new prior, something like that. Okay, but here, yeah, we're just focusing on frequencies. Yeah, we show those they are equivalent in some regards when under the linear regression model, but for survival model, they are a little bit different. Yeah.
Okay. Thank you.
Thank you.
I saw that you are planning to study some inferences involving lasso method.
Right. So for last, yeah.
So I'm sorry, you can speak.
So yeah, for lasso, yeah, people think when you have big data, you don't really need to do lasso because data are already large enough, and then you have what you want. Okay, but the thing is, sometimes when new data comes in, the variables that are important before may not still stay the same. So that's something we are working on. Right? If they are the same, then no need to do anything. No. Yeah, can just get what you want.
Yeah, I see that lasso is also related to some non-parametric methods for curve estimations, especially, I would not say especially, but including wavelet analysis, which is useful to detect, for example, irregularities of curves that you are interested. When you have some nonlinear behavior in the relation, etc. So in this case, lasso it's useful to estimate and also at the same time to regularize the estimate, the curve estimation.
Right.
So it seems to be quite interesting, maybe possible to consider some non-parametric approach in this kind of methodology?
Absolutely. And for this paper, we are not purely doing parametric, as you can see, it's semi-parametric, and also the baseline hazard for adaptive case, it's sort of like non-parametric, right? And yeah, the idea can be definitely applied to that, so that's something we are currently working on. Yes, absolutely.
Okay, let me see. Any more questions? Nope. So just one second. I will stop the recording. I forgot to do it. Just a minute.